So it's an immense honor and real privilege to be here today. I'd like to express my gratitude to the organizers, particularly Michael Berta, for the very nice introduction and for extending the invitation in the first place, and especially for organizing tomorrow's workshop. Whatever is lacking in today's talks will be more than made up for tomorrow and the next day, I'm quite sure. I'd also like to say that it's a special honor to somehow have one's name associated with the Hirschfeld lectures, not just because of the prior presenters of these lectures, but especially because of Hirschfeld himself. I know a bit more about Hirschfeld this year than I did last year because I had the special privilege of talking to Manny Parson about him in Texas A&M in the spring. It's quite a remarkable person. A thing that wasn't mentioned in the introductory lecture that was just presented is something that I didn't know was that in 1935, after being in London only a year, Hirschfeld, or as we know him in the US, H.O. Hartley, wrote a paper which is really correspondence analysis of en lettres. And it is an amazing thing for somebody to make a transition after a year and write a fundamental paper that really wasn't appreciated for another 20 years. But this accomplishment and all of his other work, and the fact that he really, at the end of his career, made amazing strides in advancing statistics as a discipline in the US, makes him a really inspirational figure. Inevitably, on such an occasion, there's a desperate attempt to discern some kind of grand design from the jumble of previous research that one has done. And it would be nice to be able to say that even as graduate students, Gib Bassett and I thought of quantile regression as some way to expand the consciousness of the social sciences, some kind of tab of LSD or something that might change the way people think about statistics and the social sciences. But it's taken a long time to get to the point where we even have a glimmer of what this might really be all about and how it could be used. But it is quite rewarding that there seems to be kind of a resurgence of interest in these kinds of methods in a variety of areas. I mean, a kind of a bewildering notion, a variety of topics are being explored, from metabolism of giant squid to intensity of tropical cyclones to analysis of microarray data and all kinds of things that are being done in economics. It wasn't always so obvious that there were these applications ready to be found. An early referee at a unnamed journal commented, "It may be of interest to compute median regression analyses to minimize the sum of absolute deviations between observed and fitted responses, but why should one consider other quantiles?" Fortunately, not everybody was so pessimistic, and I have many colleagues and collaborators to thank for their encouragement and efforts over the years. In this first lecture, I'm going to try to provide a very broad and very gentle overview of some of the motivation for and mechanics of quantile regression, and toward the end, I tried to insert two small hints about new topics that I've been thinking about as kind of future research activity, in the hope that somebody with more energy than I will maybe take them up in the future. Let's see if I can make this work. This is the straw man of the first talk, the representative consumer. alive and well and drinking in Paris. Economics and the social sciences generally have kind of put this guy front and center on a pedestal of some sort, arguing that if we could only understand his behavior, we could understand the structure of society and all its interactions. It's a kind of convenient fiction, especially from a theoretical point of view, but also from a statistical point of view, to have a kind of single figure like this that we can use to summarize everything we need to know about social interaction. But it's really hard to imagine economics in a situation in which we really have a representative agent that's acting as if the whole economy is based on his views and desires. It's clear from a lot of theoretical work that was done in the 70s, but I think underappreciated, that even basic things like demand theory that is based on this kind of notion is really relying on kind of dubious notions of how aggregation works. And as soon as one admits a certain amount of heterogeneity in preferences, then usual kinds of aggregation results are a little bit far-fetched. So there are a number of reasons, and I think I don't really need to go into them. Much more prominent people than I have really, I think, emphasized in recent years how important it is to begin to study heterogeneity in economic settings. And I'm viewing the statistical methods that I want to talk about in the coming lectures as one way to begin to do that. I mean, there are lots of other ways to begin to do that too, but I think it's important to have a diversity of statistical techniques for dealing with these issues. So I like to think of Adolf Quetelet as the father of this average man, this straw man of mine. He was originally a meteorologist by training, and I think this sort of gives you a notion that somehow enough data collection will produce whatever you need to know. And in that way, he is to social science in somewhat the same way as Alexander Humboldt, the brother of our host institution's founder or namesake, a kind of inveterate data collector and big influence over early social science. So if Quetelet constructed the average man, then in the spirit of postmodernism or something, our task is to deconstruct the average man, or maybe disintegrate him in more mathematical terminology. So every boy needs a mother, and Florence Nightingale is my candidate for the mother of the average man. Her chaste reputation, I have discovered, makes this something like a modern example of virgin birth, I would say. She really has quite an amazing statistical career that I think is unappreciated by a lot of people, and so I recommend especially a letter that she wrote that's in the back of the Pearson biography of Galton, which sort of lays out a whole research plan for the social sciences and proposes a professorship in applied statistics at Oxford. Unlike Quetelet, she seemed to actually understand that studying variability around the average was kind of a good idea. And so I kind of especially think that it's worthwhile to kind of think about her as a model. So this is a time-lapse drawing of the average man from an early Quetelet monograph. And it appears to be something like a modern growth chart. That is, you have these curves there. But if you look at it a little bit more carefully, you realize that it's not a growth chart at all. That is, it has nothing to do with the variability of height in the population. It really only has to do with the average behavior of heights in the population, and so it represents the growth of the average man and all his parts. The idealization of the average man is a curious idea, and one whose political consequences I think we've learned can be quite dangerous. It's sometimes argued that the idealization arises naturally from the model of measurement in the physical sciences, where we're entitled in some way to hope that the improvement in instruments will enable more and more accurate assessment, yielding eventually a true signal. But no amount of refinement of data on human heights, for example, will make human heights converge to a single signal with everyone of average height. And careful study of variation in heights, as we've seen over the last 20 or 30 years, has yielded some deep insights into variability in the standard of living and a variety of other issues. And so we forget this idea that statistics is really about the study of variation at our peril, I would say. This is a more modern growth chart, or what I would like to think of as a more modern growth chart. It's from a recent paper that I've done with Shuming He and Ying Wei. It's a kind of non-parametric variant of the usual growth chart that you're shown in a doctor's office. And the thing that really was a revelation to me was that if one compares the quantile regression version of this with the standard version of these methods that is widely applied by international health organizations, you see that one of the things that you see, at least, is that even after Box-Cox transformation to normality, human height data, at least at these early ages, is really very difficult to make look normal. One really needs, I think, with something as with such strong presumption of normality, to think about more flexible methods. I like to say that these growth charts are the first encounter that people have with statistics generally, and with quantile regression in particular. At birth, we emerge into the first light, and before we know what's happening, somebody's weighing and measuring us and putting us on one of these charts. And so in a certain sense, this is the quantile regression, so it was fun to work on it with Shuming and Ying Wei. So last historical figure that I'll talk about is Francis Galton, who really was the guy who painted the average man onto the target of statistical thinking. But there's a certain irony in this. I mean, he was really the inventor of the least squares regression, at least if one adopts, and I certainly do the kind of historical view of Steve Stigler. But it's kind of curious that in the work before this famous regression discovery and this famous plot that he produced that invented regression, Galton was really what I'm now liking to call a quantologue. This is my newly minted term for ideologues of this type, fixated on quantiles and distributions. At least as of a few days ago, this word had the rare distinction of being what I came to learn was called a Google whack-blat. I don't know whether this is really a German word or not, but it means a word that, a single word that produces only a single Google hit. But I'm hoping it will become a little bit more widespread word. I'm thinking about, selling membership cards in this society at the end of the workshop. But the point is that Galton, in this earlier work before regression, really was kind of unhappy with notions of moment-based summary measures of statistics, and relied entirely on medians and interquartile ranges and related things to describe statistical variability. And this is clearly the kind of forerunner of the Tukey five-digit or five-number summary, or the box plot, or a variety of things like that. Now we come to the kind of mechanical part of this, which I'll try to do rather quickly. But it is a kind of simple and kind of attractive fact of life that one can define quantiles not in terms of sorting, but in terms of just simple optimization, which leads to some nice consequences in terms of generalizations. And so this simple piecewise linear objective function then can be used to define quantiles and to generalize them to other contexts. And it may seem that this kind of piecewise linear thing, with its lack of differentiability, at least at a single point, is computationally problematic. I've tried to argue over a long period, and not very successfully, I would say, that this makes it actually a very convenient computational thing. In fact, Steve Portnoy and I have a paper that claims that in large samples it's actually easier to compute quantile regressions than it is least squares regressions. I don't think we really convinced very many people about that, but there are results to this effect. But as soon as you sort of look at the objective function for several observations, you begin to see that it really is quite smooth, and the convexity makes it quite easy to work with. There's a simple notion of how to generalize this to other contexts based on the least squares paradigm. That is, one can just observe that squared error unconditionally produces sample means or population means, and conditional means can be defined in a corresponding way by just conditioning pointwise on covariates. And one can do the same thing by generalizing the notion of the quantiles. That is, univariate quantiles can be solved by finding the minimum of this simple piecewise linear objective function, and conditional quantiles can be done that way too. So if maybe I have one other sort of slightly silly illustration of the So the geometry of least squares, you can think about it this way. You have this blue plane that represents the space spanned by the x's. And I like to talk about least squares projection as blowing into this straw at the origin and blowing up this ball that you see there, representing Euclidean distance from the space spanned by the x's. So we do this a little more, and eventually we get some picture that looks like this, and it can be, because this is supposed to be Mathematica, we can sort of tilt it and you can get a better idea maybe of what the picture is supposed to look like. And the corresponding picture for quantile regression is simply to replace this ball by this funny octahedron. And so now we blow into the straw again, but now the octahedron is getting a bit bigger, and so this is the L1 ball, and eventually the ball comes down to a quote tangency of a sort on the space spanned by the x's, and we get this exact fit to P observations, well, 2 observations in this case. I don't know whether that is helpful, but it's another way to think about the geometry. So if you think in terms of the sample space, and now we're allowed to have more than 3 observations, it's difficult to do the previous picture in more than 3 observations, obviously. But there are various other things that are important. I mean, so outliers with respect to quantiles have this nice property that the fit is insensitive to exact position. Their only fit is only interested in signs of residuals, and so this inherently provides a kind of robustness to the underlying estimation strategy. I've added this slide because it seems that there's a kind of common misapprehension on the part of people first coming to quantile regression, that somehow it can be reproduced or mimicked by doing something using ordinary regression, that is ordinary least squares regression. And the idea that people seem to have is that if you take a small region unconditionally in Y, you can look at a subset of the observations and run a least squares regression on just that subset and get something kind of sensible out of it. But if you think about trying to do that, and in this picture, the subset of observations is given by these blue points that are in some narrow Y band, now you can fit those by ordinary least squares, as Joel Horowitz is fond of saying, you can do this, but it would be wrong. So when you do this, you do get a line, the least squares line through those points, but it doesn't really correspond to anything that is a meaningful functional of the full data set. Whereas the simple median regression is an estimate that is consistent, assuming linearity of the underlying conditional quantile function in this kind of setting. So you have this red line that is actually the conditional median function. So it's kind of just a word of warning, probably unnecessary. This is my rough attempt to have a very dubious movie. So this is a kind of quadratic, the data set is basically a kind of chi-squared error with a quadratic term in each of the quantile functions. And the blue lines are all the true conditional quantile functions, and fitted lines are these red ones that always prevail for a certain interval, subinterval of 0, 1. So we just move up through the data set through a few of these, just to illustrate kind of the rough idea. When I was finishing this monograph that came out in 2005, I included several topics that I lumped together in a kind of penultimate chapter called the twilight zone of quantile regression, with somehow the idea being that I wasn't sure whether these ideas were something where we were seeing just the first light of dawn or the last light of evening. But I'm happy to say that almost all of them have turned out to be quite interesting and have really continued to be developed by other people in ways that are extremely interesting. I'm going to talk about 3 of these subtopics later, particularly the sensor data topic, this risk assessment and L1 shrinkage a bit tomorrow. But I would like to especially single out the recent work by Andrew Cheshire and Viktor Chernozhukov and others on endogeneity and instrumental variable methods, because this has turned out to be an extremely fruitful line of research that I think has really extended these methods into areas where they didn't otherwise seem to have, much future. And now I think lots of things can be done empirically that couldn't have been done without this work. So in the brief remaining time that I have for this first lecture, I'd like to describe a couple of ideas that I've been playing with. This is in the spirit of very unfinished work, but they're both topics that I take to be in some way challenges to quantile regression. That is, maybe we could do things differently, maybe even radically differently, but still get something that provides something like the original objectives that quantile regression was supposed to deliver. The first topic is what I'll call distributional regression, and the second topic is Bayesian quantile regression. What is distributional regression? Well, I'm going to take a very simple kind of setup in order to be able to do some comparisons, and then I'm going to ask a question about whether or not this can be extended in an interesting way. So I should say that there's interesting new work by Ferpo, Fortin-Lemieux, Viktor Chernozhukov has a new paper with Blaise Marie and Ivan Fernandez-Val, also suggesting distributional regression kinds of ideas in a more general context. But I'm going to do a kind of cartoon version here, I would say, in order to maybe stimulate some questions. So the idea is that we have an IID latent variable model of the usual sort. So we don't really observe these YIs, or you might imagine in the usual binary response model that you wouldn't observe them. But in fact, I'm going to assume that we do observe the latent variable YIs, but instead of actually estimating this as a quantile regression model, for example, or as an ordinary least squares regression model, the first equation, we're going to define a family of binary response models in which we're going to treat this, but we're going to define these Zi of Y's, which are just the indicator of whether the observed response, capital YI, is bigger than some cutoff, little y. So we're going to have a family of these binary response models indexed by little y. And the indexation by little y is analogous to the indexation of the quantile regression bits by tau. But instead of estimating quantile regression models, we're going to estimate these binary response models. But we're going to estimate not just a single one of them, but we're going to estimate a family of them for different y's. So earlier proposals for estimating conditional distribution functions involved estimation of conditional densities via kernel methods. It may be a dangerous thing to say here, but I'll say it anyway, that this is an approach that I regard as almost absurdly impractical in high dimensions. But binary response is at least a root-n consistent procedure, and so there's a chance that this really needs to be taken seriously. So in the simple IID setting, meaning that the UIs are IID in this latent response. So this is I mean, you could say, well, if you have IID UIs, then why aren't we estimating this by just a single M estimator, well, and, you know, finding then something else that would be more constructive to do with the rest of the afternoon. But it's usually a good idea to start with something simple, and so I'm going to focus just on this IID UI case for a moment. So if we do this, then we get this family of binary response models, and this function S is a so-called link function, or I guess maybe S inverse is a so-called link function. And it would be the ordinary link function that you would choose if you knew what the distribution of the UIs was. So then what do? Well, you then estimate this whole family of these conditional distribution functions. And standard theory for binary response gives you a large sample theory for the resulting estimators. And you get this limiting covariance matrix, which is just simply this X prime WX inverse thing. And then you can try to compare that with corresponding efficiency of quantile regression estimates by directly applying quantile regression to this first equation. So that's the program. The quantile regression large sample theory is very simple in this IID case, of course, and you just have the usual factorization in which you have X prime X inverse coming out, and the efficiency of the procedure really determined by this tau 1 minus tau over F squared term. So one can compare these two asymptotic things, or one can compare the corresponding things in simulations. I'm afraid that this isn't going to be visible except to people in the first couple of rows. This was my first attempt to do this for logistic example. So logistic examples seem to be like the first thing that one would want to try. And so the last line here, where it says n equals infinity, and n equals infinity corresponds to a particular choice of a design specification, and then a large sample estimate of what the asymptotics were saying. I've scaled all of the other entries in the table so that they're multiplied by square root of n, so they should be all roughly comparable to the large sample theory. But the message of this is that, well, especially for the the slope parameter in the regression, which is the thing that's easiest to compare, since we're really estimating exactly the same thing with both methods. The quantile regression estimates are all about 15 to 25% more efficient than the distribution regression estimates. I've done more of this. If you take the first equation in the previous slide, this thing that I keep coming back to, and think of it as some kind of like uncensored version of the Cox model, then you get a kind of binary response model, which is this Humboldt thing, which is usually called complementary log-log in the statistical literature. And you get a very similar table for that. You get a very similar table if you do the probit case, that is normal IID UI. And so the question that I would pose, I guess, is where does this 15 to 25% come from? And are there ways to really rethink the underlying structure of the specification of the model that would make the distributional regression look better? Because at this point, this isn't really a very interesting result, I would say. You would send it to a typical journal and they would say, well, yeah, you have 3 examples and you don't have a result. there is a kind of heuristic that suggests that transformation to binary response models does seem like it's a kind of reduction of the information that is inherently in the data, but it's not quite clear how one should really think about this in a more general setting. But I'm curious to explore a little more the results here. Okay, so that was topic one. And topic two is kind of grandiosely titled Towards Structural Models. And the first thing to say is that I've always viewed quantile regression as a kind of tool of exploratory data analysis. As Michael said, I spent some time at Bell Labs, not quite at the feet of John Tukey, but we were all kind of sitting in our offices in awe when he appeared at seminars or in the hallway. And I don't really take it as a criticism that this is just exploratory data analysis, or as some economists might say, just descriptive statistics, which is a really low form of statistical life in most economics departments these days. I mean, there's quite a lot of value in just descriptive statistics sometimes. But there's also this kind of sense that one needs to impose additional information on procedures of this sort, and to find some better way to think about how to do that and trying to retain at the same time some kind of flexibility that the original methods have achieved. So I'm often resorting to this defense that, well, maybe once we see the descriptive look of the data, we can find better ways to structure or to make structural models. So there's a kind of tradition of this, actually, but it's a kind of obscure tradition. I first really saw this a long time ago in a quite famous but almost long forgotten book by Brown and Atchison called The Log Normal Distribution, in which one of the techniques that they use for estimating the parameters of this, I think I'm getting slightly ahead of the curve here, so let me say a little bit more about this. So the idea here is that one can think about global models for the whole, for an entire data set or an entire response variable Y as specification of a bunch of conditional quantile functions. And so one way to think about the way to move from quantile regression towards structural models is to think about beginning to estimate, writing down structural models that might have a global interpretation and then estimating them locally in this way, quantile by quantile, and then trying to put those quantile estimates together in some way that looks roughly like GMM, that is generalized method of moments. So this could be called, or has been called actually, the method of quantiles. And the leading example, the example from this Brown and Atchison book that I referred to a moment ago, is this 3-parameter log normal distribution example. So this is a kind of famous example for Bayesians of a situation in which maximum likelihood does something quite stupid. I learned it from Bruce Hill as a graduate student, actually. And the nice thing about the method of quantiles in this context is that you can define 5 or 6 quantiles as functions of the underlying parameters alpha, mu, sigma squared, and
then you can minimize with some difficulty this kind of GMM looking expression sitting there. And you get quite good estimates, much more sensible than at least the naive version of maximum likelihood. There's a kind of slightly sophisticated version of maximum likelihood that uses, ensures that you get an interior optimum to the likelihood function, but the naive likelihood actually behaves pretty badly. So this is another slogan for the talk. Quantiles are moments too, of a sort. So another variant of this, and maybe something a little bit more practical, is thinking about specifying quantile functions of this type as in terms of linear basis expansions. And then one has the advantage that you don't have a nonlinear relationship between the parameters, the underlying parameters, theta, and the quantiles. You just have this simple linear one. And so then you can write down in closed form the least squares solution to the previous optimization problem. And there's actually a number of papers around in the last 2 or 3 years suggesting Bernstein polynomials for this basis expansion, partly I think because they have a kind of natural support on 0, 1, and partly because they can be pushed into a constrained framework where you can guarantee monotonicity. If you're just doing, univariate quantiles, you don't really presumably need to enforce monotonicity, but if you're doing some kind of regression application, then enforcing monotonicity becomes a kind of important consideration. So this is a bit more elaborated version of how one might think about this in a more Bayesian framework. There's an old idea which I think for some Bayesians probably would be scandalous, except that it was first proposed by Harold Jeffreys, and therefore it can't be scandalous. And so the idea is to think about a substitute likelihood for the quantiles. And so the first expression is Jeffreys' idea for the substitute likelihood for the median. And this can be obviously generalized very simply to a kind of multinomial setup in which you have a vector of quantiles. And this has been looked at by, in this recent paper, or not so recent paper, by Levine. And has been looked at in more detail by this paper in the recent annals by Walker. And these kinds of quote, likelihoods are eventually looking, because of Stirling's formula and the usual CLT for multinomials, looking a lot like just the asymptotic distribution of the ordinary quantiles, or in regression settings, the asymptotic distribution of the regression quantiles. And so if you think about the joint asymptotic distribution of a vector of quantile regression parameters, you can think of that as a likelihood. Well, you can in certain circumstances. I mean, you may be in trouble in certain very Bayesian environments, but there's some sense to this. And once you have this kind of likelihood, then there's an opportunity to specify prior distributions for underlying parameters, and then one is off into the world of MCMC. In settings where you really have a considerable amount of prior information and you really want a global specification that is consistent with that prior, then it seems to be a quite interesting avenue to explore. I'm relatively new to MCMC, but I'm gradually learning enough to try to mimic very simple models of this sort, and beginning to see that it has some advantages. As always, priors are good when priors are good, and when priors are bad, they can be very, very bad. But it's an approach that I think in some circumstances one really can get some real benefit out of. So to conclude, this is my short history of statistics in the 20th century. We have Sisyphus, or someone very much like him, pushing this L2 ball up this mountain, and periodically we forget certain things, usually things that were first invented by Charles Stein, and we have to reinvent them and push the ball up a bit further yet again. We've done a pretty good job of that. That is, Gaussian statistical models, I think, are in very good shape, and it's maybe time to move on to something else. And this is what I have in mind for the... So, thank you very much.
That was an inspiring introduction to a wonderful day, I'm sure. Are there any questions for Roger? I mean, he's very cool, as you can see. So, as far as questions from the audience, if there's anything that you'd like to probe him on, pushing up polyhedra up hills. Okay.
Yeah, of course.
Okay.
Roger, I have the question. You had this Bernstein polynomials, these psi functions, or how do you call that? That leads to, say, non-parametric conditional quantile estimation. And when I talk to people from the computer science, they have also invented this stuff already, but they call it support vector machine quantile regression. Could you please comment, because it was missing here, could you please comment on that? What you see as similarities and maybe computational advantages? Certainly the loss functions are different. And, you can say something.
Yeah, I'm not really terribly familiar with the support vector machine version of quantile regression. I mean, but there are.
Can you speak?
But it's there are certainly a lot of connections with what has been going on in machine learning. I'm actually quite happy to see that the computer science people are beginning to recognize that. At least conditional mean models need to be sometimes supplemented by kind of more complete distributional kinds of models. This Bernstein polynomial specification, as far as I know, doesn't really have any very close connection to the support vector machine version, but it may, and I'm just not... yeah, it is definitely the same spirit of trying to find some kind of basis expansion for functional representation, right? I might mention in that connection that Jim Ramsey has some recent work doing something very similar to this, using a little bit more open-minded is not a good phrase, but a bigger class of possible basis expansions motivated by particular families of distribution. So, if you could certainly imagine that if you really thought that you had a kind of Pearson family notion of how to expand quantile functions into basis functions, then you could use that and then try to truncate that basis expansion in some reasonable way. And Jim's very clever about inventing these kind of differential equation motivated basis expansion representations. And I think that's that's one way that one might push this forward. I mean, my sense is that the Bernstein polynomial specification per se is not terribly attractive. For one thing, the imposing monotonicity, it gives you something that's
has some serious problems that maybe I shouldn't really go into at this point. Michael?
Yeah, so I was curious your comment on distributional regression. Are you sort of like saying this is the end, or is there any hope for?
No, I think that, I mean, it seems to me that there are a lot of people interested in distributional regression, and my sense is that it must be good for something, and there must be some way to do it that's a bit different than the way that I've been looking at it through this very narrow filter of mine. And what I'm very curious to learn is, how it can really be made, I mean, I don't even really think you need to specify something like my model and then say, okay, here's a case where it works better. I think there are certain situations where maybe the interpretation of distributional regression is something that's more attractive from, say, an economic point of view, because instead of being fixated on a single quantile, which I have to admit I have been for 30 years or so, it may be better to be fixated on a certain conditional probability. And those two things are really in some way quite different aspects of the same problem. They're obviously very related, but they're in some way different, and it may be that from an interpretive standpoint it's better to do the latter. Yeah.
I have, may I? Two more questions. One is very simple. How do you explain that so many papers are written on quantum regression and much less on expectile regression? Expectile is another way of specifying the conditional distribution. And the other very short question is, you gave very nice examples from biology and medicine, and I would like to investigate whether you could give us some valuable examples, for example, finance examples.
Yeah, I'll try to say something about the finance examples, although I have to say that I'm not a finance person, so it may be that my notion of finance and other people's notions of finance don't intersect very well, but so that's at the end of the day, I guess, in this third lecture this afternoon. On expectiles, this is always kind of a tricky thing to say something about. From my point of view, the real advantage of quantiles is that they have a natural interpretation. That is, when you say tau, it means that there are a certain proportion of the observations above that and a certain proportion below. Expectiles don't have that feature. They're really a global specification in a certain sense. That is, if you say the tauth expectile and you sort of somehow wiggle the tail of the distribution up here, that expectile moves. And so the kind of robustness aspect that I referred to very briefly in the middle, it no longer is there. And to me, that really weakens the interpretability of the things. My sense was, there's a very nice, in addition to the maybe better known work by Newey and Powell, there's a very nice paper by Brad Efron using expectiles in Poisson regression type settings. But my sense from Brad about that was that he was motivated to a certain degree by the what he thought was the easier computation of expectiles, and I'm willing to accept quite a lot of the idea that expectiles might be useful for something, but I'm really not willing to accept that they're easier to compute. So if that's the motivation, then it's I think difficult to justify it. But again, for other purposes, it may be that they have actually a more natural interpretation. I just haven't really seen anything like that at this stage.
Yes?
You mentioned
Yeah.
you mentioned a couple of topics from the Twilight Zone.
Yeah.
And as it seems that there's some time, maybe you can mention upon the causal effects and IV. What are the current problems and developments?
Well, I think we'll hear more about that in the workshop by people that are much more qualified than I to talk about it. I mean, both Andrew Cheshire, who is here, and Joel Horowitz have been working on interesting variants of this. Viktor Chernozukov, I think, is also going to talk, but maybe not about IV methods. Maybe I could just mention one thing in this direction, and that is there's a kind of quite interesting recent kind of boomlet in trying to think about quantile regression in panel data models. This has been a very difficult thing for a long time. A lot of people have sort of talked about it and speculated about what could be done, but in the last, say, 5 or 6 years, we now have, 10 or 12 papers probably on the topic from different perspectives. A standard problem in dynamic panel data models in econometrics is this bias that one gets from the lagged dependent variables, and for those kinds of settings, it's important or quite useful to have IV type procedures. And the original proposal by Chernozukov and Chris Hansen seems to be quite effective in dealing with the bias problem in much the same way that standard IV methods have been effective in the usual least squares setting. So I'm hopeful that not just in the kind of causal model setting and kind of traditional simultaneous equation kind of settings, but in other places where IV methods have proved useful, that these kinds of methods will be able to be used in other settings as well. Andrew. No, I didn't. Right.
I recall that in, I think Roger Klein has some work which uses distributional regressions but transformation models. A function of a monotone function of y is x beta plus epsilon.
Okay.
What is the monotone function? And splitting things up into binaries at different levels is informative about this.
Right.
Quantile regression is very well suited to this because of this evidence. And I wonder if there is something to look at when we're thinking about comparison between what you get.
Right. Yeah, I haven't seen this paper by Roger, which is really embarrassing since we were nearly office mates at Bell Labs in the old days. But it's, one definitely is in this transformation model setting. I mean, this link function business that I was mentioning is really a kind of essential feature of the distributional regression setup, because you have to have something that maps probabilities back into the linear predictor space. And it may well be that there's some, more general version of the transformation model that's leading to something better.
I was also going to say that this might be the answer, an answer to why you wouldn't want to look at expectiles. Because they're going to be critically dependent on
Right. Yeah, that's...
Whereas it doesn't really matter if you're non-parametric with a quantile regression. You want to get to whatever transformation you want.
Right. I mean, this equivariance the quantiles themselves have this nice property that I'll talk about briefly after lunch, that the monotone transformations of the response variable at least transform into the what you're trying to estimate in a very nice way. how well you can estimate it is also somewhat influenced by the transformation, which is a slightly inconvenient aspect, but it seems to be inevitable. So one can't really expect too much, I guess, out of this. But as you say, expectiles, because they have this kind of global nature to the specification, have some difficulties with it. Michael?
I have one last question. As coming from the economics perspective, can you give us a couple of good examples for the audience of where quantile regression in practice has really brought us ahead, forward in some important data questions, be it labor economics or industrial organization, or obviously, there's nice, from the biosciences, there's some nice examples. I'm just curious.
Well, I think there are places in labor economics. I mean, duration models, which I'll talk about after lunch, I think is one place. I mean, unemployment durations is something that I think we still don't understand, but we really badly need to understand much better. I can't say that there's anything very compelling in the way of new work there that has changed how we think about these things. I don't know. There are lots and lots of examples. I think there's some work on educational effectiveness that have been somewhat helpful. I mean, I think there again, it's a place where mean models are not really very adequate to study program treatment outcome kind of things. And if you're interested in something like class size, you're not just interested in mean performance and its effects, but you're interested in the whole distribution effect. But again, I'm a little bit reluctant to cite individual work at this point.
That was great.
Okay.